Hello 171 class, this is your notes for section 2.6. 2.6 we're talking about something called a rational function. A rational function is a function where division is taking place, right? And the numerator and denominator, the two things that are being divided, are both polynomials. So the things that we've discussed in the last couple sections, 2.3 we learned about them, 2.4 we divided them. Right, and then 2.5 we found their zeros. Well, that's what we are dividing here. Polynomial divided by polynomial. Okay, the bottom polynomial can't be the zero function. Okay, that makes sense because then we'd be dividing by 0. And then what we're going to find as we move forward is that the bottom thing not only cannot be the zero function, it can't ever be 0. It can't have an output of 0. So x that makes this thing 0, that x is not in the domain of this function because it causes division by 0. So it goes back to something we did earlier when we found domains of functions. We just didn't call them rational functions at the time. We were just learning to find their domain. Now we're actually going to study them and go beyond finding their domain and graph them. So we've already done some of these types of problems down here. But now we're going to actually go a little bit further and graph these things. So let's find the domain of these. So A, if you recall, this thing is, we divide by 0 when x is 3. So 3 can't be a part of the domain. So the way we write that is negative infinity to 3 union 3 to infinity. So the left side is negative infinity, the right side is positive infinity. Everything else is fine here except for 3. So we restrict 3. Alright, now you may be looking at that and thinking, well, can't you factor that to x plus 3, x minus 3, and then the bottom x minus 3 would cancel, and wouldn't that take away this restriction? The answer to that is no, because the way this problem was presented to us was in this non-factored form. Alright, so x cannot be 3 because the way that was presented as 3 causes division by 0, even though that thing would reduce if we canceled, or if we tried to simplify that expression. Alright, I've got the function in here, x squared minus 9 divided by x minus 3, and I'm going to graph it and hit zoom 6 to make sure I'm in the standard window. Alright, there's what I get. And if I hit trace, remember trace puts a cursor on the graph. If I go to 3, see here the y output's blank. Y output is 0. If I go to something like 2 point a whole bunch of 9s, I get an output 6. Okay, or virtually 6, really close to 6. And if I put in something like 3.00000001, again I'll get 6. So that's would be basically where it was. Again, if we look at what this thing reduces to, just x plus 3, if I plug in 3 there, the restriction, 3 plus 3 is 6. And that's what we're getting. We're getting something really, really, really close to 6. But we can't plug in 3, right? It should look like it was 3 because I put in so many zeros. But I can't actually put 3 into this thing because it's restricted the way it's written. Okay, it would reduce to something where 3 would be restricted. That's not the way it was written to initially, so that's what we have to go with. So 3 is restricted. It's not in the domain. Okay, so keep that in mind. It doesn't matter for domain. It doesn't matter if it cancels. You still have to reduce. You still have to restrict it even if it does reduce away. Right here, it does not reduce away. Nothing reduces away. So this still does simplify to, or factor to x plus 3x minus 3. And now both of these are set to 0. And so we now have to restrict positive 3 and negative 3. So remember, the way we write restrictions when there's more than one is we go from negative infinity to the lowest, which is negative 3. Then union lowest to the other restricted value, union the other restricted value to infinity. Okay. Now, this, when I graph it, now when I graph this one, you'll see this crazy looking thing going on here. Alright, what's really important for you to understand with these graphs of rational function, alright, move over here now, is that these lines right here are not actually there. You guys that have a TI-84 or newer version of TI-84s especially, you won't see that line right there. Okay, it's called a vertical asymptote. It's actually dashed. It's not really there. But this graph is hugging the x-axis, and it's bending right here, and it's going down, and it's going off the screen. Okay, we don't actually see it, but it actually is doing that, just like it is right here on the other side. It's going up off the screen, and it's crossing, going down, hugging the asymptote. And the same thing here. This one's so steep we can't see it. The TI series calculators have a very hard time graphing vertical line. Well, they can't graph vertical lines in this mode that they're in. So when these things turn and start rising so steeply that it's virtually vertical, it's not perfectly vertical, but it almost is, the calculator just can't handle it, and it just leaves things blank. So this is actually what that graph looks like. Okay, but again, what do you see? You see that a big difference between what is actually supposed to be there and what you get to see. So you have to learn the way these things are going to look on your own, so you are able to graph them accurately. All right, and then the third one, x squared plus 9. Remember, if you notice what we're doing here, to find the domain. So for domain, think denominator. So we're setting the denominator equal to 0 for these rational functions. So again, we've done it before, but that's how we find the domain of a rational function. So if I set x squared plus 9 equal to 0, that means that x squared was equal to 9. Or sorry, negative 9. And that can't happen. With real numbers anyway. And yeah, if we allow imaginary numbers, we know that we can do that, but we can't have a negative number come out of a real number squared. So the domain here is all real numbers. Right, if we can't get a 0 for the denominator, we don't have to worry about restrictions here. That's the only type of restriction we'll have in this chapter. We're not going to have to worry about square roots of negatives like we talked about before. So the domain not being 0 means that you aren't going to have any restrictions. So negative infinity to infinity is your domain. All right, another thing that we use for rational functions, because of these asymptotes, because of the graph taken off towards infinity, is something called arrow notation. All right, arrow notation, we say a variable heads towards some value, right? Or a variable heads towards infinity, or variable heads towards negative infinity. And then if it's going towards a value, then we say, all right, which direction is it approaching the value? So we're approaching from the right. If we have a little plus superscript up here, we're approaching from the left if we have a little negative superscript. So let's look at this graph we have down here and make sure we understand it. All right, so as x approaches 0 from the left, all right, here's 0. We're approaching 0 from the left. That means we're coming in this way. Where is the function headed? It's the height of the graph. The closer and closer and closer I get to 0, the height gets higher and higher and higher and higher and higher up. So what we're being asked to do here is, it's basically saying, as we make our way to 0 from the left, how is the height off the x-axis? What is it approaching? And it's just getting higher and higher and higher. Because of the arrow, we know that it's going towards infinity. All right, then on the other side, it's saying, as we approach 0 from the right side. Right, the plus means now we're approaching from the right side. Where is it headed? And again, you see it gets higher and higher and higher and higher. So we're again headed towards positive infinity. Right? Without bound, that just means it's never going to stop getting bigger. Alright, and then the other way, as x makes its way to infinity or negative infinity, think of this just means the right side of the graph. This means the left side of the graph. So as we make our way to the left side of the graph, as x is going this way, where is the function headed? Okay, so it's had a height of 1, had a height of like a half, a tenth, a hundredth. Alright, it's just getting smaller and smaller and smaller. So it's headed towards 0, okay, the x-axis. And as we make our way to the right side of the graph, as we go this way, alright, where is f of x headed? So x is headed towards infinity. That's just always getting bigger with the numbers, so we're making our way to the right side. The same thing happens. We get smaller and smaller and smaller with our heights. So we're headed towards 0. Alright, let's practice it again. As x heads towards infinity, f of x heads towards 0. Okay, again, we see we're headed towards 0. Alright, as x heads towards negative infinity, to the left, f of x is also headed towards 0, but notice it's headed from the bottom. It's headed from the below the x-axis, but it's still headed towards 0. So like negative 1, negative a half, negative a tenth, negative a hundredth, negative a thousandth. So it's getting closer and closer and closer to 0 as we make our way to the left. Alright, as x heads towards 0 from the left, so there's 0, we're making our way towards 0 from the left. The graph is headed towards not infinity this time, but negative infinity. Okay, we're going down forever as we get closer and closer and closer to 0. Alright, as we make our way to 0 from the right, this time we're coming in this way. We're getting higher and higher and higher. So it's approaching positive infinity. Alright, the minus superscript and the plus superscript from the left, from the right. Now you use arrow notation a lot in calculus. You'll get to see it a lot in calculus, but here we typically only use it briefly just to talk about asymptotes. So a vertical asymptote is a vertical line, okay, x equals a. That's a vertical asymptote if, as x approaches a from the left or the right, we take the graph itself takes off towards infinity or it takes off towards a negative infinity. Okay, this is what it's going to look like when you get to calculus. Everything's going to be limits. The limit as we approach a from the right is infinity. Okay, that's the notation that you'll get used to as you make your way from pre-calculus to calculus. But right now, just know this top line, as we approach a from the left, from the left side, we're taking off towards infinity. We approach from the right side, we're going towards negative infinity. We approach from the left side, we're going towards negative infinity. So any of those situations, if we're going towards infinity, negative infinity, it doesn't matter from the left or right. If that takes place, then that line is a vertical asymptote. Alright, now well, how do we find a vertical asymptote? I mean, obviously, if we have the graph, we can see, if I had this graph, yeah, I can see that x equals 0 is a vertical asymptote. But what do I do mathematically to find one? Well, you factor these two numerators and denominators, these two polynomials. Factor them as much as you can. Cancel any common factors they have. And the remaining factors in the denominator, you set equal to 0 and solve. The solutions to the remaining factors in the denominator set to 0 are the vertical asymptotes. Okay, now, right here, any common factors that cancel, the ones from the denominator that cancel, which it have to be in the numerator and denominator to cancel, this is the location of holes in the graph. So that's important too. You'll need to know where there's any holes in the graph. So anything that cancels out was a hole. Anything that remains is an asymptote. Alright, so these are what we're talking about, asymptotes. That's what vertical asymptote is, basically what division by zero looks like. We can actually see division by zero when we see a vertical asymptote on the graph. Alright, so look at these three graphs right here. This is x divided by x squared minus 9, what we saw before. There's our vertical asymptotes. Let me move this down a little. This is x plus 3 divided by x squared minus 9. Alright, and then this is x plus 3 divided by x squared plus 9. Again, we don't see any vertical asymptotes. But let's look right here. If we factor the bottom and get x minus 3, x plus 3, because that's the difference of squares, nothing cancels. And because nothing cancels, that means there are everything that makes the denominator 0 is a vertical asymptote. Alright, so I factored, I tried to cancel, nothing cancels. I set each of these factors equal to 0 and solve. So this would be x equals 3. This one's x equals negative 3. Okay, so here's x equals negative 3, the vertical line. Here's x equals positive 3. Remember, x equals a number is a vertical line. Here, x squared minus 9, when I factor it, I get x minus 3, x plus 3 again. But x plus 3 will cancel. So x minus 3 is the only thing that remains. That's the only thing I set equal to 0. So x equals 3. There's the only vertical asymptote. The other one, x plus 3, is not a vertical asymptote. Alright, if you count it over, negative 1, negative 2, negative 3, there's actually a hole in the graph. Right there. Okay, but it's not a vertical asymptote. Alright, here's that same graph on my calculator. You can see that, but if I hit trace and type in negative 3, again, see, it doesn't give me any output. There's a hole there. I know there's a hole there if I can do something like negative 2.9999, something really close to negative 3, and it gives me output. Alright, so that's a hole if it doesn't break apart and do like this. Notice when I plug in positive 3, it gives me no output, but when I plug in something really close and get closer, notice this number right here gets further and further and further away from the x-axis. Alright, now we're at 1,000. Alright, now we're at 100,000, so it's getting further and further and further away. Whereas the other one, again, if I did like negative 2.999, the number is going to get closer and closer and closer to a number. Alright, it's getting closer and closer and closer to negative 1/6, which is the output if I plug in a negative 3 here. 1 over negative 3 minus 3 is negative 6, so 1 over negative 6, negative 1/6. That's what would be there if we had reduced this expression beforehand and plugged in negative 3, but we didn't. So instead of getting negative 1/6 out, we actually get a hole in the graph. And then right here, this is a sum of squares, so it doesn't factor. And since it doesn't factor with real numbers, that is, I can't make this equal to 0. So it's not going to have any vertical asymptotes. Alright, and you'll see as you go through the notes, I use VA to represent vertical asymptotes. So this has no vertical asymptotes. And you can see from the graph, it doesn't break apart. Also has no holes in the graph. Alright, now that doesn't mean that anything that has no vertical asymptotes will always have no holes. If, for instance, the very first example that we looked at, the x squared minus 9 over x minus 3, when we factored that x minus 3 canceled. So we ended up with just an x plus 3 on the top. That did not have a vertical asymptote, okay, but it did have a hole. So again, it's not mutually exclusive. Like, you know, if this happens, then this also has to happen. You can have vertical asymptotes only, you can have holes only, or you can have a mixture of both, like we have right here.